Hello. All right. Another night where we're gonna continue learning our transformers. I just want to finish up this 3 blue 1 brown transformer video. Um, so yeah, that's what I want to do today.
NFT is
And then,
smaller.
okay, so yeah, we understood softmax, and then we're
In the
getting
last
to
chapter, you and I
attention,
started
how
comments
attention
have
works.
in
So there's
France and
QKV,
in
right? And the query matrix, the key and the value. So keys are answers to the queries, and then values, I don't know where those come in.
made of steel. If it was also preceded by the word miniature, to step through the computations though, let's take a much simpler example. Imagine that the input includes they also encode the position of the word to represent tend. The goal with those right now, we're laser focused on the nouns. At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces a much smaller dimension than the embeddings in the arrow. That question is somehow encoded as yet another vector, another list of numbers, which we call the query for this word. This query vector, though, has a much smaller dimension than the embedding vector, say 128. Computing this query looks like taking a certain matrix, which I'll label WQ, and multiplying it by the embedding. Compressing things a bit, let's write that query vector as Q. And then anytime you see me put a matrix next to an arrow like this one, it's meant to represent that multiplying this matrix by the vector at the arrow's start gives you the vector at the arrow's end. Any vector in head-learn, true behavior is learned from data, and in practice, what this matrix does in a particular attention head is challenging to parse. But for our sake, imagining an example that we might hope that it would learn, we'll suppose that this query matrix maps the embeddings of nouns to certain directions in this smaller query space that somehow encodes the notion of looking for adjectives in preceding positions. As to what it does to other embeddings, who knows? Maybe it simultaneously tries to accomplish some other goal with those. Right now, we're laser focused on the nouns matrix. At the same time, associated with this is a second matrix called the key matrix, which you also multiply by every one of the embeddings. This produces a second sequence of vectors that we call the keys. Conceptually, you want to think of the keys as potentially answering the queries.
Is there a Coforce round tomorrow? I really need to do a Coforce round. 1002. Okay, the next one's a div 4. Div 1 and 2. In a week and a half. Wow.
This key matrix is also full of tunable parameters, and just like the query matrix, it maps the embedding back to the query matrix query the adjectives like flapreacher. To measure how well each key matches each query, you compute a dot product between each possible key query pair. I like to visualize a grid full of a bunch of dots, where the bigger dots correspond to NaPluffy and Blue really do align closely with the query produced by Creature. Then the dot products in these two spots would be some large positive numbers. In the lingo, machine learning people would say that this means the embeddings of Fluffy and Blue attend to the embedding of Creature. By contrast to the dot product between the key for some other word, like the.
Like, shouldn't you normalize it? My question is, yeah, like, this, it tells you the similarity, but like, that's just because of the angle. But you could have like two vectors like that. One's like super big, and even though their cosine is almost equal to 0 because the magnitude is so big, it's similar to every other vector. Like super is almost dot product is the vector the so yeah, I think you should normalize it.
And the query for creature would be some small or negative value that reflects that these are unrelated to each other. So we have this grid of values that can be any real number from negative infinity to infinity, giving us a score for how relevant each word is to updating the meaning of every other word. The way we're about to use these scores is to take a certain weighted sum along each column, weighted by the relevance. So instead of having values range from negative infinity to infinity, what we want is for the numbers in these columns to be between 0 and 1, and for each column to add up to 1, as if they were a probability distribution. If you're coming in from the last chapter, you know what we need to do then. We compute a softmax along each one of these columns to normalize the values. In our picture, after you apply softmax to all of the columns, we'll fill in the grid with these normalized values. At this point, you're safe to think about each column as giving weights according to how relevant the word on the left is to the corresponding value at the top. We call this grid an attention pattern. Now, if you look at the original transformer paper, there's a really compact way that they write. Each time they're about to use these scores, and people would say that this means the embeddings of Fluffy and Blue attend to the embedding of creature. By contrast, the dot product between the key for some other word, like the, and the query for creature, would be some small or negative value that reflects that these are unrelated to each other. So we have this grid of values.
Okay, I guess the dot product can be negative because cos of a large angle can be negative.
From negative infinity to infinity, giving us a score for how relevant each word is to updating the meaning of every other
And you take a softmax?
The way we're about to use these scores is to take a certain weighted sum along each column, weighted by the relevance. So instead of having values range from negative infinity to infinity, what we want is for the numbers in these columns to be between 0 and 1, and for each column to add up to 1, as if they were a probability distribution. If you're coming in from the last chapter, you know what we need to do then. We compute a softmax along each one of these columns.
Because take
to normalize the values. In our picture, after you apply softmax to all of the columns, we'll fill in the grid with these normalized values. At this point, you're safe to think about each column as giving weights according to how relevant the word on the left is to the corresponding value at the top. We call this grid an attention pattern. Now, if you look at the original transformer paper, there's a really compact way that they write this all down. Here, the variables q and k represent the full arrays of query and key vectors respectively, those little vectors you get by multiplying the embeddings by the query and the key matrices. This expression up in the numerator is a really compact way to represent the grid of all possible dot products between pairs of keys and queries. A small technical detail that I didn't mention is that for numerical stability,
I guess like in this case, query is like this, and then key is like this, and then that computes the dot product of the query. Did he flip this around? Like, because Q2, Q3, Q4, because this should be like KQ, the dot product of KQ, because it's row times column, right?
it happens to be helpful to divide all of these values by the square root of the dimension in that key query space. Then this softmax that's wrapped around the full expression is meant to be understood to apply column by column. As to that V term, we'll talk about it in just a second. Before that, there's one other technical detail that so far I've skipped. During the training process, when you run this model on a given text example, and all of the weights are slightly adjusted and tuned to either reward or punish it based on how high a probability it assigns to the true next word in the passage, it turns out to make the whole training process a lot more efficient if you simultaneously have it predict every possible next token following each initial subsequence of tokens in this passage. For example, with the phrase that we've been focusing on, it might also be predicting what words follow creature and what words follow the.
Oh.
This is really nice because it means what would otherwise be a single training example effectively acts as many. For the purposes of our attention pattern, it means that you never want to allow later words to influence earlier words, since otherwise they could kind of give away the answer for what comes next. What this means is that we want all of these spots here, the ones representing later tokens influencing earlier ones, to somehow be forced to be 0. The simplest thing you might think to do is to set them equal to 0, but if you did that, the columns wouldn't add up to 1 anymore. They wouldn't be normalized. So instead, a common way to do this is that before applying softmax, you set all of those entries to be negative infinity. If you do that, then after applying softmax, all of those get turned into 0, but the columns stay normalized. This process is called masking. There are versions of attention where you don't apply it, but in our GPT example, even though this is more relevant during the training phase than it would be, say, running it as a chatbot or something like that, you do always apply this masking to prevent later tokens from influencing earlier ones. Another fact that's worth reflecting on about this attention pattern is how its size is equal to the square of the context size. So this is why context size can be a really huge bottleneck for large language models, and scaling it up is non-trivial. As you might imagine, motivated by a desire for bigger and bigger context windows, recent years have seen some variations to the attention mechanism aimed at making context more scalable, but right here, you and I are staying focused on the basics. Okay, great. Computing this pattern lets the model deduce which words are relevant to which other words. Now, you need to actually update the embeddings, allowing words to pass information to whichever other words they're relevant to. For example, you want the embedding of fluffy to somehow cause a change to creature that moves it to a different part of this 12,000 dimensional embedding space that more specifically encodes a fluffy creature. What I'm going to do here is first show you the most straightforward way that you could do this, though there's a slight way that this gets modified in the context of multi-headed attention. This most straightforward way would be to use a third matrix, what we call the value matrix, which you multiply by the embedding of that first word, for example, fluffy. The result of this is what you would call a value vector, and this is something that you add to the embedding of the second word, in this case something you add to the embedding of creature. So this value vector lives in the same very high dimensional space as the embeddings. When you multiply this value matrix by the embedding of a word, you might think of it as saying, if this word is relevant to adjusting the meaning of something else, what exactly should be added to the embedding of that something else in order to reflect this? Looking back in our diagram, let's set aside all of the keys and the queries, since after you compute the attention pattern, you're done with those. Then you're going to take this value matrix and multiply it by every one of those embeddings to produce a sequence of value vectors. You might think of these value vectors as being kind of associated with the corresponding keys. For each column in this diagram, you multiply each of the value vectors by the corresponding weight in that column. For example, here, under the embedding of creature, you would be adding large proportions of the value vectors for fluffy and blue, while all of the other value vectors get zeroed out, or at least nearly zeroed out. And then finally, the way to actually update the embedding associated with this column, previously encoding some context-free meaning of creature, you add together all of these rescaled values in the column, producing a change that you want to add, that I'll label delta E, and then you add that to the original embedding. Hopefully, what results is a more refined vector encoding the more contextually rich meaning, like that of a fluffy blue creature. And of course, you don't just do this to one embedding, you apply the same weighted sum across all of the columns in this picture, producing a sequence of changes. Adding all of those changes to the corresponding embeddings produces a full sequence of more refined embeddings popping out of the attention block. Zooming out, this whole process is what you would describe as a single head of attention. As I've described things so far, this process is parameterized by 3 distinct matrices, all filled with tunable parameters: the key, the query, and the value. I want to take a moment to continue what we started in the last chapter with the scorekeeping, where we count up the total number of model parameters using the numbers from GPT-3. These key and query matrices each have 12,288 columns, matching the embedding dimension, and 128 rows, matching the dimension of that smaller key query space. This gives us an additional 1.5 million or so parameters for each one. If you look at that value matrix by contrast, the way I've described things so far would suggest that it's a square matrix that has 12,288 columns and 12,288 rows, since both its inputs and its outputs live in this very large embedding space. If true, that would mean about 150 million added parameters. And to be clear, you could do that. You could devote orders of magnitude more parameters to the value map than to the key and query. But in practice, it is much more efficient if instead you make it so that the number of parameters devoted to this value map is the same as the number devoted to the key and the query. This is especially relevant in the setting of running multiple attention heads in parallel. The way this looks is that the value map is factored as a product of 2 smaller matrices. Conceptually, I would still encourage you to think about the overall linear map, one with inputs and outputs both in this larger embedding space, for example, taking the embedding of blue to this blueness direction that you would add to nouns. It's just that it's broken up into 2 separate steps. The first matrix on the right here has a smaller number of rows, typically the same size as the key query space. What this means is you can think of it as mapping the large embedding vectors down to a much smaller space. This is not the conventional naming, but I'm going to call this the value down matrix. The second matrix maps from this smaller space back up to the embedding space, producing the vectors that you use to make the actual updates. I'm going to call this one the value up matrix, which again is not conventional. The way that you would see this written in most papers looks a little different. I'll talk about it in a minute. In my opinion, it tends to make things a little more conceptually confusing. To throw in linear algebra jargon here, what we're basically doing is constraining the overall value map to be a low rank transformation. Turning back to the parameter count, all 4 of these matrices have the same size, and adding them all up, we get about 6.3 million parameters for one attention head. As a quick side note, to be a little more accurate, everything described so far is what people would call a self-attention head, to distinguish it from a variation that comes up in other models that's called cross-attention. This isn't relevant to our GPT example, but if you're curious, cross-attention involves models that process 2 distinct types of data, like text in one language and text in another language that's part of an ongoing generation of a translation, or maybe audio input of speech and an ongoing transcription. A cross-attention head looks almost identical. The only difference is that the key and query maps act on different datasets. In a model doing translation, for example, the keys might come from one language, while the queries come from another, and the attention pattern could describe which words from one language correspond to which words in another. And in this setting, there would typically be no masking, since there's not really any notion of later tokens affecting earlier ones. Staying focused on self-attention, though, if you understood everything so far, and if you were to stop here, you would come away with the essence of what attention really is. All that's really left to us is to lay out the sense in which you do this many, many different times. In our central example, we focused on adjectives updating nouns, but of course, there are lots of different ways that context can influence the meaning of a word. If the words, they crashed the preceded the word car, it has implications for the shape and the structure of that car. And a lot of associations might be less grammatical. If the word wizard is anywhere in the same passage as Harry, it suggests that this might be referring to Harry Potter. Whereas if instead the words Queen, Sussex, and William were in that passage, then perhaps the embedding of Harry should instead be updated to refer to the prince. For every different type of contextual updating that you might imagine, the parameters of these key and query matrices would be different to capture the different attention patterns, and the parameters of our value map would be different based on what should be added to the embeddings. And again, in practice, the true behavior of these maps is much more difficult to interpret, where the weights are set to do whatever the model needs them to do to best accomplish its goal of predicting the next token. As I said before, everything we described is a single head of attention, and a full attention block inside a transformer consists of what's called multi-headed attention, where you run a lot of these operations in parallel, each with its own distinct key, query, and value maps. GPT-3, for example, uses 96 attention heads inside each block. Considering that each one is already a bit confusing, it's certainly a lot to hold in your head. Just to spell it all out very explicitly, this means you have 96 distinct key and query matrices, producing 96 distinct attention patterns. Then each head has its own distinct value matrices, used to produce 96 sequences of value vectors. These are all added together, using the corresponding attention patterns as weights. What this means is that for each position in the context, each token, every one of these heads produces a proposed change to be added to the embedding in that position. So what you do is you sum together all of those proposed changes, one for each head, and you add the result to the original embedding of that position. This entire sum here would be one slice of what's outputted from this multi-headed attention block, a single one of those refined embeddings that pops out the other end of it. Again, this is a lot to think about, so don't worry at all if it takes some time to sink in. The overall idea is that by running many distinct heads in parallel, you're giving the model the capacity to learn many distinct ways that context changes meaning. Pulling up our running tally for parameter count, with 96 heads, each including its own variation of these four matrices, each block of multi-headed attention ends up with around 600 million parameters. There's one added, slightly annoying thing that I should really mention for any of you who go on to read more about transformers. You remember how I said that the value map is factored out into these two distinct matrices, which I labeled as the value down and the value up matrices. The way that I frame things would suggest that you see this pair of matrices inside each attention head. And you could absolutely implement it this way. That would be a valid design. But the way that you see this written in papers and the way that it's implemented in practice looks a little different. All of these value up matrices for each head appear stapled together in one giant matrix that we call the output matrix, associated with the entire multi-headed attention block. And when you see people refer to the value matrix for a given attention head, they're typically only referring to this first step, the one that I was labeling as the value down projection into the smaller space. For the curious among you, I've left an on-screen note about it. It's one of those details that runs the risk of distracting from the main conceptual points, but I do want to call it out just so that you know if you read about this in other sources. Setting aside all the technical nuances, in the preview from the last chapter, we saw how data flowing through a transformer doesn't just flow through a single attention block. For one thing, it also goes through these other operations called multi-layer perceptrons. We'll talk more about those in the next chapter. And then it repeatedly goes through many, many copies of both of these operations. What this means is that after a given word imbibes some of its context, there are many more chances for this more nuanced embedding to be influenced by its more nuanced surroundings. The further down the network you go, with each embedding taking in more and more meaning from all the other embeddings, which themselves are getting more and more nuanced, the hope is that there's the capacity to encode higher level and more abstract ideas about a given input beyond just descriptors and grammatical structure. Things like sentiment and tone, and whether it's a poem, and what underlying scientific truths are relevant to the piece, and things like that. Turning back one more time to our scorekeeping, GPT-3 includes 96 distinct layers, so the total number of key, query, and value parameters is multiplied by another 96, which brings the total sum to just under 58 billion distinct parameters devoted to all of the attention heads. That is a lot, to be sure, but it's only about a third of the 175 billion that are in the network in total. So even though attention gets all of the attention, the majority of parameters come from the blocks sitting in between these steps. In the next chapter, you and I will talk more about those other blocks, and also a lot more about the training process. A big part of the story for the success of the attention mechanism is not so much any specific kind of behavior that it enables, but the fact that it's extremely parallelizable, meaning that you can run a huge number of computations in a short time using GPUs. Given that one of the big lessons about deep learning in the last decade or two has been that scale alone seems to give huge qualitative improvements in model performance, there's a huge advantage to parallelizable architectures that let you do this. If you want to learn more about this stuff, I've left lots of links in the description. In particular, anything produced by Andre Karpathy or Chris Olah tend to be pure gold. In this video, I wanted to just jump into attention. in its current form, realizable, I think produced by Andre Carpathy or Chris Ola, tend to be pure gold. In this video, I wanted to just jump into attention in its current form, but if you're curious about more of the history for how we got here and how you might reinvent this idea for yourself, my friend Vivek just put up a couple videos giving a lot more of that motivation. Also, Britt Cruz from the channel The Art of the Problem has a really nice video about... If you feed a large language model the phrase, Michael Jordan plays the sport of blank, and you have it predict what comes next, and it correctly predicts basketball, this would suggest that somewhere inside its perceptron. At this point, the problem is that this operation is purely linear, but language is a very non-linear process. If the one that takes all of the negative values and maps them to 0, and leaves all of the positive values is 1, if and only if the full name is Michael Jordan, and 0 or negative otherwise, after you pass it through the ReLU, you end up with a very clean value where all of the 0 and negative values just get clipped to 0. So this output would be 1 for the full name Michael Jordan and 0 otherwise. In other words, it very directly mimics the behavior of an AND gate. Often, models will use a slightly modified function that's called a JLU, which has the same basic shape, it's just a bit smoother, but for our purposes, it's a little bit cleaner if we only think about the ReLU. Also, when you hear people refer to the neurons of a transformer, they're talking about these values right here, and you add on a certain bias term. In this case, the number of dimensions in the output is back down to the size of that embedding space, so I'm going to go ahead and call this the basket do, but you can feel free to ignore it for now. Making our notation a little more compact again, I'll call this big matrix W down, and similarly call that bias vector B down, and put that back into our diagram, like I previewed earlier. What you do with this final result is add it to the vector that flowed into the block at that position, and that gets you this final result. So for example, if the vector flowing in encoded both first name Michael and last name Jordan, then because this sequence of operations will trigger that AND gate, it will add on the basketball direction, so what pops out will encode all of those together. And remember, this is a process happening to every one of those vectors in parallel. In particular, taking the GPT-3 numbers, it means that this block doesn't just have 50,000 neurons in it, it has 50,000 times the number of tokens in the input. So that is the entire operation. 2 matrix products, each with a bias added, and a simple clipping function in between. 8. Multiplying those together, of each neuron tells you how much a given vector extra wiggle room to fit more vectors in, which makes it all the more counterintuitive that for higher dimensions, the answer changes anything from 0 to 180 degrees, but you'll notice that already, even just for random vectors, there's this heavy bias for things to be closer to 90 degrees. Then what I'm going to do is run a certain optimization process that iteratively nudges all of these vectors so that they try to become more perpendicular to one another. After repeating this many different times, here's what the distribution of angles looks like. We have to actually zoom in on it here, because all of the possible angles between pairs of vectors sit inside this narrow range between 89 and 91 degrees. In general, a consequence of something known as the Johnson-Lindenstrauss lemma is that the number of vectors you can cram into a space that are nearly perpendicular like this grows exponentially with the number of dimensions. This is very significant for large language models, which might benefit from associating independent ideas with nearly perpendicular directions. It means that it's possible for it to store many, many more ideas than there are dimensions in the space that it's allotted. This might partially explain why model performance seems to scale so well with size. A space that has 10 times as many dimensions can store way, way more than 10 times as many independent ideas. And this is relevant not just to that embedding space where the vectors flowing through the model live, but also to that vector full of neurons in the middle of that multi-layered perceptron that we just studied. That is to say, at the sizes of GPT-3, it's in range. Is that the zoom in on it is a lot of perpendicular. This is very significant for large population, would be way more than 10 times it was doing that. What it means is that individual features aren't going to be visible as a single node. If you're curious to learn more, a key relevant search term here is sparse autoencoder, which is a tool that some of the interpretability people use most that made this. At this point, we haven't touched every detail of a transformer, but you and I have hit the most important points. The main thing that I want to cover in a next chapter is the training process. On the one hand, the short answer for how training works is that it's all backpropagation, and we covered backpropagation in a separate context with earlier chapters in the series. But there is more to discuss, like the specific cost function used for language models, the idea of fine-tuning using reinforcement learning, which you may have heard the phrase, the unreasonable effectiveness of mathematics in the natural sciences. The tool for doing that is an integral, as a quick reminder, applying this curve by a different number. So it's the same basic shape, just scaled down by that number, meaning its area is the same as our mystery constant, just scaled down by some number. That's pretty cool. Each one of these slices has the same basic shape. We saw earlier feel a little bit less out of the blue. I mean, a key problem-solving principle in math is to use the defining features of your setup. And if you had been primed by this Herschel-Maxwell derivation, where in the last
I've been working on this project about visually explaining transformers. As he said, I love visually explaining all sorts of things, usually in math, but I'm happy to spread into the adjacent fields. The target audience here is always a little bit tricky, because I know many of you are engineers and are quite technical, but I don't necessarily want to assume too much background from people. The one thing I will assume is that you're maximally curious, that you're hungry to dig into the details of what's going on. For example, I think most people know that large language models consume a lot of computation, they take a lot of resources, fit into an n-dimensional space so that every pair is 90 degrees apart. The reason this would be relevant, if you want distinct directions in the space to correspond to distinct ideas, if they're perpendicular, that helps you from having unwanted overlap. And for example, if you have some direction that corresponds to the idea that the words being spoken are in German, and then some other direction corresponding to the idea that the general tone of speech is one of skepticism, you don't want those to align over each other, because that would mean that any time that you're speaking German, it accidentally infers that it must be skeptical in some way. Maybe that one's not a bad idea. It's that language models. Every pair is perfect. A slightly related quiz, which is to say, how many vectors can you fit into an n-dimensional space? Not so that every pair is perpendicular. If you think it doesn't give you that much, the number of dimensions. In case of say 1,000 dimensions or 10,000 dimensions. When I was playing with 100-dimensional vectors, I could definitely comfortably fit like hundreds of thousands in that would be quite close to each other. But it's shocking. It might explain a couple different things. One, it might explain how these models can actually fit quite a few ideas into a seemingly small space. Small in the sense of, compared to the number of concepts in the world, 12,000 isn't that big. And also why they scale surprisingly well, because you don't really get this effect of exponential growth kicking in until you get to a certain dimension. And so as you go from, say, 10 to 100 dimensions, it's not just that you're getting 100 times as many directions at your disposal, you're getting many more than that. And so that to do this, like I said, is by telling a little bit of a lie for, or 120 context ones, and then there's going to be many different layers of attention. So if this is just one of the heads, multi-headed attention is something where you think about those happening all in parallel. And again, the mantra for transformers is that they're very well architected to work on GPUs, so that you can run these things. I follow the question. So you're saying that the trend where residual networks, for example, came to be quite helpful. Is there something like that in the case?
Yes.
I mean, the residuality is sort of baked in from the beginning with how it's even done. The thought that as you're going from layer to layer, rather than generating an entirely new
Transformations. But you're not really interested in the absolute values that you calculate in each transformation. Wouldn't be the mix of analog computers together with digital ones resolve this energy hungriness?
That's a good question. I am not an expert on that, the drawbacks or advantages of analog computers, and therefore I should stop talking now. But in principle, like from a first principle standpoint in physics, it does make a lot of sense where if you're more error tolerant in that way, like the advantage of digitization over analog computers, if you were to go back to the 1940s and explain to someone like why they should bet on one horse and not another, has to do with error propagation. And so in this case, if kind of don't care about that because everything's just a matter of soft association anyway, I'll believe it. I am as curious as you are to understand why that's not the case. I know.
And text and sound are basically one dimension in some sense because you read from left to right or you listen.
Yeah, I think the Letitia's
Okay,
lecture is
so
going
let's
to be
start
better.
explaining the transformer architecture. Transformer are stacked. Hello everyone, this is not an AI copy break, it's rather an entire lecture about large language models or short LLMs, because today we want to give you an overview
I think
of
it
all
was
things
too
you know
abstract
about
for some of the
large language
concepts, and it
models
was not deep
today.
enough.
So the third of the lecture will be about the transformer architecture, because transformers, established 2017, have been making the backbone of LLMs since then, and it's been the tricks that have been established starting 2020 that have made transformer LLMs reach the caliber of ChatGPT, and with that made it into journalistic headlines, but most importantly, brought LLMs into everybody's hands, because I don't think I need to ask you whether you use any large language model today, like for example ChatGPT, Claude, Llama, or many others. So here I list the contents in detail that we are going to cover, and it's not to intimidate you with this entire list, but it's rather to help you navigate the video. We will use chapters to tag every content we will explain. So if you think, I want to learn something about tokenization, then you can jump there in the video, or if you say, I want to learn something about retrieval augmented generation or instruction tuning and so on, you can jump there in the video. So to set your expectations, in this video we have compiled and broken down all the components you need to understand about LLMs of today, but let me tell you, making and editing a video like this takes a lot of skill from me, and skill like this I needed to train, and luckily I had Skillshare on my side to help me level up. Skillshare, by the vectors or models. Okay, so let's start explaining the transformer architecture.
So there's attention, an attention layer, then there's an MLP, then attention to MLP, right?
Transformer are stacks of identical transformer layers. Like in any deep learning architecture, we stack layer after layer after layer because we hope that we will get better output representations from input representations. For transformers, input representations are vectorial. In general deep learning, you can have vectors or higher dimensional vectors, namely matrices, or higher dimensional matrices, namely tensors. But for transformers, it's the easiest form you almost can imagine, namely these vectors. And we apply layer after layer after layer such that, hopefully, these representations in the end are better representations than the representations we have started with. What does it mean for representations to be good? Well, it means that here the solution space is representing, obviously, the solution to our problem. Or in deep learning terms, it means that this representation space is linearly separable with respect to our task. So to explain that, let's first define a task. Like what could here a task be? Well, we're making large language models, so let's think of a simple low-dimensional task. To visualize, we want to decide whether the word well is a plausible continuation of sentences like this. So can we replace the CLS with well, yes or no? That's basically our binary decision task we have here. And for this solution space to be obvious means that we have a linearly separable space, namely in which all sentences, so the classification token, the CLS representation for all sentences that end with well are on one side of the space, and the representation of the CLS token of all sentences that do not end well, pun intended, are on the other side of the representation space, such that we can use just the linear separation to distinguish such sentences when we look at the classification token. So here I've taken the liberty to represent this four-dimensional space as a two-dimensional space, but I've done it just for visualization purposes. There is no dimensionality reduction here, and this is what we expect from these better representations after all the transformer layers. And for the initial representations, we expect such a space not to be linearly separable, so the solution to our task of whether well is a possible continuation of this sentence is not obvious over here. Yeah, so that's why we do all of these transformer layers to get better representations. And in short, transformer layers map L d-dimensional vectors into other L d-dimensional vectors. Okay, but now that we know that transformer layers take as input vectors, the natural question that arises for language models is how to represent text as vectors. Text is discrete, text is symbolic, and vectors are continuous, so how to transform that? Well, we can use a naive idea and we can see how far we can get with a naive idea until we have to fix it. Namely, we can first look at all the words we have in a training corpus and make a vocabulary. Then we have here mother and attention and any other word we have encountered in our training data, and we can make a dictionary out of it. So we give to every word a word ID, and to each word ID we give a unique word embedding. The question is which unique word embedding? It doesn't matter, one can initialize it randomly and we can update these word embeddings during training. But then the obvious problem with this is that we will have a finite training corpus. So at test time, when users interact with such a model, we will have the trouble of new words, some words that simply haven't been in our training corpus, and also obviously there will be typos, because people are very bad at writing, there will be typos in there, and all of these new words will map to an unknown token and will have the same word embedding, and this is not a good semantic representation for such unknown words. So we have to somehow have a tokenization strategy such that new words will also get as semantic representation as possible. So the solution here is tokenization. Tokenization means that we compose the vocabulary now out of subwords, which we will call tokens, and the idea is to have common words end up as part of the subword vocabulary, but to split rarer words into subcomponents, and these subcomponents are sometimes unintuitive, but this is the idea. For example, we split mom into MOM, and M gets the M26 token ID, this other M the same token ID, and then they will get the same word embeddings, and so on. And in the worst case, basically each character in the word will become a subword. Okay, but then how to tokenize? What is the algorithm that splits us all these words into subwords? Well, tokenizers are many. There's, for example, byte-brain coding, which I will explain because it's one of the most popular tokenizers these days, used by Llama, for example. And here, the tokenizer has a training stage. This training stage of a tokenizer is very different from the training of our deep learning model of our transformer. It happens way before that. So here, the training of our tokenizer, we basically define a target vocabulary size. We say we want 50,000 tokens in our vocabulary. And then we start with a set of all characters as individual tokens. And here, to be honest, it's not characters. In byte-brain coding, it's bytes, so it's 0 to 255. And one can represent every character as bytes, or as multiple bytes. And then progressively, we merge the most frequent token pairs occurring together in the training data and store the resulting new token and the merging rule, and the training is completed when the desired number of tokens is reached. So to encode text with such a trained tokenizer, BPE basically splits the input into individual characters, and as I said, this is not exactly characters, it's bytes, and then applies the lowest ranking merge rule until no more are applicable. And there's many other tokenizers other than byte-brain coding. There's unigram, sentence piece, character-based, n-gram-based, and so on. And the interesting is that for a while, the research on tokenizers was kind of boring, not much was happening, but especially in 2024, the research on tokenizer has exploded, and especially there's many approaches now to be a little bit more tokenizer-free. So and if you're interested in that, I can make a dedicated video about that, so let me know in the comments. Okay, so now that we have an idea about how we can represent text as vectors, our transformer layers are happy as long as they get vectors as input, and we can see what this transformer layer is all about. So let's build the transformer layer from its fundamental components. We will start by adding a very familiar component to deep learning enthusiasts, namely the feed-forward neural network, also called vanilla neural network or fully connected neural network. So basically, this feed-forward neural network is applied to every token in our input, and it's always the same neural network that is applied to every token. And how does it look like? Well, basically, we have one multi-layer perceptron layer that is doubling the dimensionality of the input dimensionality and followed by a gel activation. And then we have another layer here that is downsizing the input back to the original dimension. And most importantly is that there's here the concept of weight sharing, namely that we have the same weights that we apply to this token, the same weights applied to every other token. And this concept of weight sharing, maybe you know from convolutional neural networks, but it's basically a very important concept in transformers too, because if you share weights like this and you have the same neural network applying in parallel to each of these tokens, you can do all these computations of all these tokens in parallel. This is very much different from the recurrent neural networks that were processing the first token, and then the output of the first token somehow was going into the input of the second token, meaning that the second token had to wait for the computation of the first token to finish in order to continue processing and then so on. So if you sequentially read Wikipedia, maybe you're done in a few weeks reading in such a way. So language models before they were transformers, they were this recurrent neural network based, but they took a lot of time to process text like Wikipedia. And then when transformers came, they could run all these computations of multiple tokens in parallel, meaning that you could suddenly read Wikipedia in much less time than recurrent neural networks. And if you were like, oh, okay, after a few days, I've already read Wikipedia, then let's read some news, let's read some more articles, let's read books, let's read the entire internet. So the architectural superiority of transformers is basically this parallel computation that allows the transformer neural network to see much more data in a much faster time than recurrent neural networks did before. And usually for these networks, the more data and the better data you can ingest, that's where the capabilities of the models come from. So this is here the important concept of weight sharing and of parallel computation in transformers. So now we will close this visualization here and we will summarize all the weights that we have seen before in such a box for the feed-forward neural network. And now the question is whether we're done with our transformer architecture. And the obvious answer is no, because there's some very important component missing here, namely a way for letting this token here, for example, know that it shares some company. That here works is not a word that is in isolation, because this feed-forward neural network will act on these representations in isolation from all the other representations. This is not good. This representation cannot be a better representation of words because it has no notion of the company it keeps. And it's a very important concept in distributional semantics that words are very much defined by the company they keep. So we need a mechanism to let information flow between tokens and let tokens and representations know of the company they keep. And for that, a mechanism that is very much used by the transformer is the self-attention mechanism. Self-attention is a weighted averaging, but it's a very important weighted averaging because the data-dependent weighted averaging. So self-attention basically tells us that to compute the representation of this token, we will get 80% from this token, 15% of this token, and 5% of these tokens. And it will do this weighted averaging here. But very important, and that's why self-attention is so powerful, is that these weights for the weighted averaging are not somehow determined in advance. They are data dependent. So this 80% depends very much on the representation of attention and the representation of words. So let's see how that works. And first, let's see what is the difference between self-attention and attention. Self-attention is when we compute attention between one sequence and basically itself again. So here, for computing attention for the token A, we will look at all tokens in the same sequence and see that, okay, we have to take, in our averaging, a lot of the value of this one and a lot of the value of this one and not so much of the others. That is self-attention, when we compute attention in the sequence within itself. But then attention is when we have the same mechanism basically, but between a sequence and another sequence. And here attention, for example, is very much used in machine translation, where we have the sentence in one language and the same sentence in another language. And here we compute how much for computing the representation of this one, we have to take information from this other sentence. Okay, but here in the normal transformer layer we have self-attention, and self-attention basically tells us how much we need to do data-dependent weighted averaging. So let's see how we can compute this data-dependent weights for this averaging, and this is basically just a lot of linear algebra, which I know it will be a little bit complicated, but we've tried to make it as simple as possible. Okay, so for that, let's zoom into self-attention. In self-attention, the first thing we need to do is to take the representation of a token, x1, and multiply to a so-called query matrix. Now the question is, how does this query matrix look like?
What's
Well,
a
it has
KV
to have the right
cache?
shape.
KV caching. Wow.
Transformers are used almost everywhere in natural language processing. Model and you cannot generate any more aggressive decoding. Instead of passing in a host.
But other than that, it's randomly initialized, and then process of learning and stochastic gradient descent will update the entries of these matrices. So we have the query matrix, and we multiply to the representation of our input token, and we will get a vector called query. And we do the same thing, we apply the same matrix, again weight sharing, we apply the same query matrix to all the other representations from our input. Then we're done with generating our queries, so now we have queries for every input token. Now we'll go to keys. So now we will have a different matrix called a key matrix with different values than the query matrix, also randomly initialized, and it will be learned during training, that we will multiply to the representations of our input and we'll get keys. So here's a key for the second token and so on. And then, if we're done with that, we'll also take a value matrix and we'll multiply to all the input representations, and then we'll get values for each representation in our input. Okay, and maybe you have already noticed the mistake that was here in the slide. If not, I'll fix it for you right now. So here, to really get the multiplication right, we need to put these matrices on the right, otherwise the multiplication doesn't work. But in any case, after we do the multiplication right, we will get these query, key, and value matrices for each of these input tokens. And after we have generated the keys, queries, and values, we can a little bit forget about the matrices that have been producing them and see what we will further do with these query, keys, and values. For the sake of the visualization, let's see how we can compute attention. Based also randomly, other representations from our input. Then we're done with generating our queries. So now we have queries to weighted averaging. So let's see how we can compute complicated, but we've tried to make it as simple as for this averaging, and this is basically just a lot of linear algebra, which I know it will be a little bit complicated, but we've tried to make it as simple as possible. Okay, so for that, let's zoom into self-attention. In self-attention, the first thing we need to do is to take the representation of a token, x1, and multiply to a so-called query matrix. Now the question is, how does this query matrix look like? Well, it has to have the right shape, but other than that, it's randomly initialized, and then process of learning and stochastic gradient descent will update the entries of these matrices. So we have the query matrix, and we multiply to the representation of our input token, and we will get a vector called query. And we do the same thing, we apply the same matrix, again weight sharing, we apply the same query matrix to all the other representations from our input. Then we're done with generating our queries, so now we have queries for every input token. Now we'll go to keys. So now we will have a different matrix called a key matrix with different values than the query matrix, also randomly initialized, and it will be learned during training, that we will multiply to the representations of our input and we get keys. So here's the key for the second token and so on. And then, if we're done with that, we'll also take a value matrix and we'll multiply to all the input representations, and then we get values for each representation in our input. Okay, and maybe you have already noticed the mistake that was here in the slide. If not, I'll fix it for you right now. So here, to really get the multiplication right, we need to put these matrices on the right, otherwise the multiplication doesn't work. But in any case, after we do the multiplication right, we will get this query, key, and value matrices for each of these input tokens. And after we have generated the keys, queries, and values, we can a little bit forget about the matrices that have been producing them and see what we will further do with these query, keys, and values. For the sake of the visualization, let's see how we can compute attention for this word now words, but we can do it the same as a representation in our input. Okay, and maybe you have already noticed the mistake that was here in the slide. If not, I'll fix it for you right now. So here, to really get the multiplication right, we need to put these matrices on the right, otherwise the multiplication doesn't work. But in any case, after we do the multiplication right, we will get this query, key, and value matrices for each of these input tokens. And after we have generated the keys, queries, and values, we can a little bit forget about the matrices that have been producing them and see what we will further do with this query, keys, and values. For the sake of the visualization, let's see how we can compute attention for this word now works, but we can do it the same for attention, and usually in a transformer one does it for every input token, but just to simplify the presentation, we'll do here for works. So what happens here is that we take the query and we multiply the query of this token of interest with the keys of every other token in the sequence, including itself. So we will take query 2, multiply the key 1, and we will get a certain value, let's say 2. It's just a scalar product between this and this vector. Then we'll take this and this vector, we'll do the multiplication, and then we'll take this and this vector, and we'll do the multiplication, and we'll get some certain values that can be outputted by the scalar product. Then what happens is a division by the dimensionality of the vectors. Here we say that dimensionality is 3, so we will divide this by square root of 3, and the same will do for every other multiplication here. And then the important thing happens, it's a nonlinear function that we apply here, namely the softmax. The softmax will take care of producing values between 0 and 1 from all these values here, and also values that sum up to 1. So you can also interpret them as percentages. It means basically that here we have a 13% attention score, here we have a 78% attention score, and so on. And this is now the weights we
Lutetia, this doesn't sum to 100%.
we use for our data-dependent weighted averaging. Data-dependent because these weights now have been computed from the data itself. This query vector and this key vector, they come from multiplying the matrix with these vectors here. So now we're ready to do the data-dependent weighted averaging. We take these weights here and compute a weighted sum. So to get a new representation for works, we make a weighted sum of the values of each of the tokens by using the weights that we have computed for that token. So here 13% is for the first token, so we will take 13% of the value of the first token, we will take 78% of the value of the second token, and so on. And now the question is, how do we jump from a 3-dimensionality to a 4-dimensionality? Well, because here I have no more space to write it, but here basically we have another matrix multiplication that will map from the dimensionality of 3 to the dimensionality of 4 back to our original representation space. So that is basically what happens in self-attention. We compute new representations for the token works by taking the certain amounts of weights that are data dependent, that have been generated by multiplying query, key, and value matrices to these vectors here. We add the values of these tokens up with respect to the coefficients here that we have calculated, with the weights that we have calculated, and we will get a final representation of works, the same. So here the final representation is the final representation that we will get out of this self-attention layer. And what we did for the token works, we can do for every other token. So after the self-attention layer, we will get new and better informed representations for every other token. And now these representations are better because they're informed by the company they keep. Okay, so this was the self-attention mechanism. And after we have understood this, we can ask ourselves, are we done with the transformer architecture? And the answer is not quite, because something is missing, something very important is missing. Because if we look at the representation of this CLS token here, when we have this input works attention, it will be the same as when we have the input attention works. And the question is, how can that be? Well, it can be because this feed-forward neural network will do its computation independent of every other token. And it can also be because the self-attention mechanism here is basically commutative. It's permutation invariant because we have here a summation which is commutative. We have here these multiplications which are again commutative. So all in all, the self-attention layer and the feed-forward neural network, all in all, they're permutation invariant, meaning that the result here doesn't change with respect to the order of the input sequence. And this is back because language is very much dependent on the order of the sequence. It's not the same in other modalities, but in most modalities like language and images, order matters. If you scramble up the order of pixels in an image, it won't be the same image anymore, and you won't understand that it's a cat over there. So we need a way to somehow tell the network that this is the first token, this is the second token, this is the third token, and this is exactly why positional embeddings are a very important part of the transformer architecture. So what are these position embeddings? So here we have the semantic representation of the token, and here the position embedding is basically like the house address. So if we say we are on street number 1, and very important is that if here we have a different word, the semantic embedding will change, but the position embedding will stay the same. If this position embedding will also always comes to anything that will be on first position, and then we have another position embedding, other values here for the second position, and so on. So how do these position embeddings look like? Well, in the attention disordered paper, the one that introduced the transformer, the position embeddings were sinusoidal. And the sinusoidal position embeddings give a different value for the dimension of the vector, depending on the index of the sequence. Here you see there's some sines and cosines. The question is why sines and cosines? Well, because they have this nice predictive structure, and the idea is that eventually they will start repeating, helping with out of distribution length. So if you, for example, train your transformer with a maximum sequence length of 1,000, there were no longer sentences or sequences in your text than 1,000. Then if you go to 1,001, the positional embeddings might be out of distribution, but here with sines and cosines, hopefully they will not be out of distribution because they will start repeating eventually. Unfortunately, this doesn't work that well with generalization, but in any case, that was the idea behind sines and cosines. And then you can ask why is here division by 10,000? Why do we have to have this power of 2 and so on? And the idea is that, well, I mean, there are some heuristic behind this, but mostly it's 10,000 because 10,000 works well in the experiments. And why not another value? Well, there might be another value with other hyperparameters. So here the idea is why let us humans engineer nice positional embeddings when one can also learn position embeddings from the data. So in the same way in which we update here the semantic embedding every time we will compute the loss function, we also update the position embedding for number 1 and then for the position embedding for number 2 and so on. So that's the idea of the position embedding. They are very popular for vision transformers, for example, so transformers that work on image data. Then there's also rotary positional embeddings, which are very popular for large language models right now, which have a huge inspiration in electrodynamics. Basically, the idea is of a linearly polarized electromagnetic wave, so a little bit like science here, but then they will be passing a quarter wave plate at a 45-degree angle, and then this wave will get a rotation, will get a phase shift. So that's basically the idea behind rotary positional embeddings. If you're interested in it, read more here. It doesn't matter how you do it, what you need to have is a way to represent position. So as long as you have a position that doesn't change here, when semantic changes, it always stays the position for 1, you are good to go and have a transformer architecture where you have broken the symmetry of permutation invariance. Now you don't have permutation invariance anymore, and now you will be able to encode order. And with that, we're almost done, because all we also need to have is these residual connections, which maybe remind you of ResNets, maybe not. But here the idea is to take the input to a sublayer and add it to the output of the sublayer again. And we
I'm getting tired again.
do this for the self-attention sublayer, we do this for the feed-forward network sublayer, and because we are adding here all the time this result of the layers to the input again, we will get always larger and larger and larger vectors with each increasing layer, which will become a problem eventually, because optimizers of today work very well in the range 0 and 1, but if we have numbers that increase and increase and increase, they will eventually be larger than 1. So the idea is here to normalize after adding these vectors that shall be staying in the range 0 and 1. And you can ask, why do we have these residual connections? Why do we even add them? Well, they help against vanishing gradients, because let's say here that on this branch we have a vanishing gradient during backpropagation. It will not vanish eventually because we have the residual connection which we can use to skip the vanishing gradient with. And also because we're always preserving information from the layer from above when we get to the output of the sublayer, this helps and increases the depth of the transformer. So we can add more and more and more sublayers and layers one after the other, meaning that we will get deeper and deeper layers. Deeper layers means that we can make the representation better and better and better, and break down the problem of getting better representations into multiple steps instead of just a few steps. And if you ask how large are, or how deep are such transformer networks, well, I mean 6, 12, 24, 48 are common number of layers for transformers, but if you want a very deep transformer, there's a paper scaling transformers to 1,000 layers that basically increase the layer depth to 1,000, but of course have to decrease this hidden dimensionality quite a lot to still fit it into modern GPUs. So this was the transformer layer with all its important components, the semantic representations of every individual token in our input sequence, then the position embedding, the self-attention layer that will contextualize these vectors, will basically get us better vectors that are informed of the neighborhood of the company that the token keeps. Then we have the residual connection, we add the input to the layer back to the output of the layer. We need to normalize the values between 0 and 1. Then we have the feed-forward neural network that will process these tokens individually. We have the residual connection where we add this input to the sublayer, we output again, we need to normalize, and these are the outputs of the transformer layer. And now the question is how to generate language from this, how to learn these vectors. This is what we'll discuss in the next chapter of day, namely the architectures of large language models. I hope you had a little break after we have had such an intense walkthrough through the transformer architecture, because now we're going to get into all the details of how to put these transformer layers and how to train them such that we can generate language from them. So let's talk about the two main ways of doing self-supervised learning on text. Self-supervision means that we don't have humans annotate our data. We don't have, for example, labels. We don't say this sentence here is positive or this sentence here has a negative sentiment. We just have data. We just have text lying around, and we use the data itself as labels to learn something from the data. And for who's one of the, let's say, 60,000 tokens or words in our vocabulary penalized in such mass language modeling fashion are called usually transformer encoders, or actually encoders for the reason we'll see later. And notable examples of that are BERT, Roberta. So if you see BERT in the name, it's usually transformer encoders. And the other very successful way to do it is autoregressive language modeling. Here, the objective is to complete the text, is to make very huge autocompletes, like we have the cat sat, and the model has to say on the mat. And here the model again predicts the text, is a classification setting again, because it has to choose which of the 60,000 tokens in our vocabulary are good to put after these previous tokens. So the loss function is again the cross entropy, and it's autoregressive because the model kind of eats its own output again. So if the model says cat after the, it will ingest cat against input to generate from the cat sat, and it will take its output as input again, and it will be the cat sat, and so on. And you see the pattern here, and that's what we call autoregression. And transformers which implement such autoregressive language modeling are called transformer decoders, or also autoregressive decoders, or also called the transformer for a reason that you will see in a bit. And notorious examples of this are the GPT family. Okay, so here I put again the transformer layer in all its details, because from now on we will abstract away all the details of the transformer layers, and we'll just say that we have L such transformer layers in an architecture, and we, of course, like for every transformer layer and transformer, we get here, for example, 4 input tokens, and we will get 4 representations out of it. And first, we're going to explain the transformer decoder. So how does a decoder generate language? Well, it has here a linear layer. And why is it linear? Because what we want to do in deep learning is to apply all these heavy layers such that these representations have the solution obvious. Obvious means we just need a linear decision to decide for the answer to our problem, here generating the next token. So we have a linear layer that will produce probabilities for each of the 60,000 tokens in our vocabulary. Here I didn't list 60,000 tokens, just a few of them. So how exactly is this done? Because training and inference, so test time, are very different. I go one by one and first start with training. How is this thing training? In training, we have the entire sentence or the entire sequence. We take chunks of text from the internet and we put them all here. Here we imagine that our transformer can just take a maximum of 4 tokens, but usually these transformers can take 512 for the BERT model, or 1024, or 128,000 for the most modern LLMs. But because we have this entire text and we want the transformer decoder to predict this text, we kind of mask it. It's called causal masking, namely in the self-attend.
Okay, I think I'm done for tonight. Didn't learn too much. I think I really just need to start implementing this, or like watch Carpathes and then learning KV cache. Like if I watch Carpathes video,
Hi everyone. Match the cross entropy obviously is garbage, inefficient, more general. Okay, and the last note at this stage is from an optimization issue, input. Now the rows are not going to be normalized by default. We're going to model with roughly 300,000 tokens. Now when you go to the GPT-3 paper, and
is his name going to be on there?
now when you go to the GPT-3 paper,
I guess Carpathes didn't work on GPT-3 because he was at Tesla.
and you look at the transformers that they trained a number of transformers of different sizes, but the 1 trillion and above. So they are training a significantly larger model on a good chunk of the internet, and that is the pre-training stage. But otherwise, these hyperparameters should be fairly recognizable, so they can predict each. Okay, and that's everything that I wanted to cover for today. So we trained, to summarize, a decoder-only transformer following this famous paper, Attention is All You Need, from 2017. And so that's basically a GPT. We trained it on a tiny Shakespeare and got sensible results. All of the training code is roughly 200 lines of code. I will be releasing this code base. So also it comes with all the git log commits along the way as we built it up. In addition to this code, I'm going to release the notebook, of course, the Google Colab. And I hope that gave you a sense for how you can train these models, like say GPT-3, that will be architecturally basically identical. Hi everyone. Hi everyone. Okay, so at this point we have the GPT. One more quick note before we continue here. I just want to point out that the relationship between weight decay, learning rate, batch size, the atom parameters beta 1, beta 2, we'll do that next. So let's now take a look at what datasets were used by GPT-2 and GPT-3. So GPT-2 are shared across all of the rows, and then we have the 4 options: model and big.
Wow.
So the first thing I would like to do is actually start at the end, at the target. So in other words, let's load.
I feel like I need to do this. Like, this is pretty fundamental. This 4 hours, oh my god. Okay. Alright, let's see.